talk, and I think we haven't had public talk for a while. So today, okay, in conjunction with the announcement of the Nobel Prize for Physics 1 month, which was won by three physicists, Penrose, Genzel, and Ghez, for their work in black holes and gravitational physics. Dr. Lin Yan-King from Department of Physics is giving us a talk about this work. So Dr. Lim, the speaker, he graduated from National University of Singapore in 2015, and then he joined Xiamen University, Malaysia ago in 2018. Dr. Lim's research basically is in black holes and gravitational physics, and he has published more than 15 papers in Physical Review, a top journal in the field of physics, theoretical physics. Okay, and let's welcome Dr. Lim to tell us more about these black holes.
Okay, thanks, Prof. Teo, and good afternoon, everyone. Welcome. So everyone can see my screen, right? I will start the talk now. So I'm here to talk about the essentially I'm here to talk about black holes, and particularly in the context of the Nobel Prize that was awarded in the last month. And the prize being awarded is about something about a theory and something about the observation. So what I will talk about today is these two things, right? From theoretical aspects and the observational aspects of the black hole. Although before I begin, I might need to put some disclaimer to say that I am a theoretical physicist, so I mostly know this part about black holes, the theory. For observations, not so much. So maybe in case there are any colleagues who are joining, who are more familiar to me, feel free to jump in. But otherwise, so I'm here to talk about these things, and also because the theory part, this talk will be more biased towards my perspective in my corner of the research field. Some of them are relevant to, and some of them are popular enough that everyone has heard of before. I will mention them, and there are some things that are very, very interesting, but not many people heard about. So I will try to share some of this with everyone today. So today's talk will be split into 4 parts. So the first one is the theory of black holes. So before we understand why is the Nobel Prize being awarded for these two particular works, we need to understand what is a black hole, how does it work, and all those things. Then the second part is about orbits around the black hole. So this is where half of the Nobel Prize is being awarded to Ghez and Genzel. So I'm going to talk about that. And then the third part is about the black hole singularity. The second half of the prize is awarded to Roger Penrose. And here I will explain what is a black hole singularity, what is it about, why is it bad, why is it problematic, and things like that. And if I have any time remaining later, I will talk about other related kinds of research, and in particular, what are the future directions of research that we are going on. So let's go to the first part, right? So part 1, right? Black holes in theoretical physics. By the way, if you see equations, right, don't worry. For today's talk, I'm not solving equation. Usually for me, public talk, I put equation for decorative purposes, right? It looks nice, so I just put it there. And I'm going to talk about the basic idea of the black hole, right? Just the concept. So to understand black holes, right, we need to understand them as gravitational objects, right? So what we're talking about is gravity. And so for the case of black holes, to understand how does black hole works as a gravitational object, we should ask the question, what does it take in order to escape a gravitational system, right? Such as a planet or a star, and also the black hole. So black holes, stars, planets, galaxies, these are all gravitational objects. I'm full screen on my computer, but you guys can see my face, right? But yeah,
yes, we can see.
You can see my face, right?
Yeah.
Okay, so by the way, if anyone have any question, feel free to chime in or type it in the chat. I will check occasionally. So, but let me continue. Okay, so we are talking about gravitational system, And what does it take to escape a gravitational system? So take an example. We are on Earth right now, right? So everyone here is on Earth, and we are experiencing Earth's gravity. So Earth is exerting the force of gravity on everything. So if we everything will get pulled towards the Earth, right? So that one is, we know this from everyday experience. So how do we try to escape from the gravity of the Earth? We can try to throw the thing up a little bit, right? So if we throw the thing up, we can see that it will travel up a little bit before being pulled back down again. Fine, never mind. We try harder. So we try to throw something as fast as we can. So we imagine that to escape the Earth, there must be some velocity that if you can eject it fast enough, it should be able to completely escape from the gravity of the Earth and therefore being launched into space. So this is what rockets do, right? So that's why you need rockets. A rocket is the rocket engine, is able to produce a thrust force that could accelerate an object fast enough to escape from the gravity of the Earth, right? Yeah. So by the way, I saw some of my mechanics students here, right? We were just talking about rockets in the previous class. So yeah. And also, for the case of the Earth, right, we can actually calculate the escape velocity. To escape our Earth, right, we know our Earth's mass, we know the size of the Earth. We need to travel at 11.2 kilometers per second in order to completely escape from the Earth, right? So that is the escape velocity for the Earth. Okay, now let us continue to the next part of this story. This is still the Earth, it's still a planet, it's not yet a black hole. But let us imagine, right, if we compress the Earth into half the size, right, compressing the Earth, so same amount of matter and mass. So we take everything, the same things of the Earth, the rocks, the same mountains and the buildings and things like that, and then we squeeze it into half the size, sorry, right? If it's half the size, okay, we can actually calculate again the escape velocity is actually higher than previously. And it is understandable because if we are compressing everything into half the size, then all the masses here are more concentrated. Therefore, the gravity here will also be more concentrated. So the force of gravity is stronger. So stronger gravity, you need a faster speed to escape from the Earth, right? So this is the situation. So then let's continue on this line of thought. So if we imagine we compress it even more, right? Keep on compressing even more and more compressed, the gravity gets even stronger and stronger. Therefore, the escape velocity becomes higher and higher. And in the end, it will reach a situation where it is something that is so concentrated and so compressed that the escape velocity is something faster than the speed of light. Now, what travels faster than light? Nothing, right? So nothing can travel faster than light, so nothing can escape from this type of object. So if not even light, if the gravity is so strong, right, if not even light can escape from this object, then there's no light. We can't see it. So it's blackness, which is why we call this the black hole, right? So one word summary of what I just said is, black hole is an object where the gravity is so strong that nothing can escape from it, right? So this is the black hole. It is a gravitational system, right? So this is hopefully to clear some misconception that a lot of people think that black hole is like a vacuum cleaner kind of thing, but vacuum cleaner, you need air, right? So black hole here, the interaction is gravitational. So again, right, I have an equation here, but don't worry, I'm not solving equations here. What I want to say with this is that historically, black holes are first predicted before being discovered to actually exist in space. So we discover them by solving Einstein's equation, right? So yeah, so once you solve Einstein's equation, we get a bunch of equations describing space-time, and then later it was interpreted to be black hole. So I'm going to talk more about it in the next few slides. So in the next few slides, I'm going to talk about the different kinds of black holes that we know about in the literature. These two are the most famous ones and probably the ones that everyone has heard about. So the first solution, the first black hole solution which was found by solving Einstein's equation is found by Carl Schwarzschild in 1916. So the very same year Einstein published his theory of relativity. And unfortunately, he also died in the same year. This time was during World War I. So his solution describes a perfectly spherical black hole. So it's just a perfectly round spherical black hole. It is the simplest solution. and it's just a black hole that is static and non-rotating. Okay, so that is Schwarzschild's solution. Now, the next black hole, right, is this the type of black hole that is most likely to exist in space is the Kerr black hole. So this was solved by Roy Kerr in 1963. It describes a rotating black hole, so meaning it carries angular momentum, right? So the picture I drawn here is that the picture is a bit flattened. Is one of the things I want to convey today is that black holes sometimes behave like everyday objects. So if you take something and then you spin it, right, it will tend to flatten along the axis of rotation, right? We also know this by experience. For example, if you are cooking roti canai, for non-Malaysians, let's say pizza dough, right? So if you take a pizza dough, you flatten it and then you spin it, you will try to flatten out. So black holes will undergo the similar behavior. Okay, so these are the common types of black holes that can exist, and the most famous ones. So next is these are probably a bit less well known, but these are also obtained by solving Einstein's equation. So one I want to mention is called black dihole, which is a pun because this is analogous to a dipole, but this is for black holes. And it's basically describing two rotating black holes on top of each other. I cite here the paper by Roberto Emparan, but there are also works by others such as Banco and Ruiz and Sipgatulin and around the 90s, and the first and Walker in the 80s as well. So this is describing two rotating black holes. Another black hole that is interesting to me is the C metric. So this solution describes an accelerating black hole. So what you have here basically is you have a Schwarzschild black hole that is perfectly spherical, but if you accelerate this system, right, if it undergoes acceleration, then you see that the shape will also deform, right, as if it's like a water droplet. Okay, so this is the C metric, and it's actually quite an old solution found in 1918, but the interpretation that it is just a mathematical solution, but it's not until the 1970s that people realize that the equation is actually describing a black hole under acceleration. So one of the lessons I guess we learn from here is that there's a math part and there's a physical part, right? So once you solve a bunch of equations, sometimes you still need an extra work to get the physical interpretation to understand what you have. Another class of black holes that can exist is more interesting if you include a negative cosmological constant. Don't care what it means. What I just saying is that if we slightly modify Einstein's, we can get more types of solutions and more different types of weird black hole shapes and things like that. So such as the topological black holes by Wanzhou in 1997 and Hubeni and others. They have if you allow black holes to be having infinite size, and it will become a surface of all kinds of shapes and geometry. So you can have things like the black funnel, and a planar black hole such as this, but in a deformed shape, and then you have a black droplet and things like that. And at this stage, I can't resist mentioning my PhD thesis. So we also found weird shaped types of black holes. This is what we found when I was working with postdoc Chen Yu and our supervisor Edward Teo. So this is also very interesting in the way black holes behaves like water. Okay, so let's take a planar black hole, right? Such as the Wanzhou one, right? It's a black hole, but it's like very large size. So you can imagine like zooming into a Schwarzschild black hole. If you get closer and closer, it looks like very very big, right? So now let us give the system an acceleration. So let us imagine that this system is undergoing some acceleration. So if the system is accelerating downwards, like in the picture here, the plane will start to deform because of the acceleration. And if we accelerate faster and faster, we see that the deformation will grow larger and larger, right? It will grow a blob shape coming out. And if we continue to increase the acceleration, this blob will start to pinch off and disconnect from the rest of the system, and it will separate off into an isolated piece over here, and leaving behind the rest of the surface. So this is the phenomena that happens if you give it an acceleration. So when I talk about it in the context of black holes, right, it sounds very weird and exotic, but we've seen things like this before in our everyday life, right? Like water. So this is exactly what not exactly, but analogous to what happens when with water. So imagine, right? Let's say if you're not talking about black hole, but this is the water on the surface of your skin. Okay. So if your hands are wet, right? So if your hands are wet, what do? You want to dry it, right? And instead of wiping it, let's say you shake your hands dry. So when you shake your hands, you are giving it an acceleration. So what is happening when you're shaking your hands is that the layer of water on top of your skin is on an accelerating hand, and therefore the water will start to clump together, and eventually it will pinch off and disconnect from the rest of the surface. So this is how you shake off water, right? So interesting, right? So black hole behaves almost similarly to fluids in that sense, and well, at least to me, I find this very interesting. Okay, so yeah, so these are like all the exotic types of black holes that not many people may have heard of. But going back to reality, right, because today's talk is going to be about the Nobel Prize for black holes that is observed in space. So let us go back to the fairly normal black hole. Let's take the terrestrial black hole and try to understand the important features at different distances from it. So starting from the center, so let's say this is a terrestrial black hole, all right? Or it could be a Kerr black hole, is almost similar. Inside the black hole, right at the center, for the terrestrial black hole, we have something which is a singularity, which I will explain at length later in this talk, right? But going out to this distance, okay, so on this layer, this is what we call the event horizon. So I have been talking about how the black hole is, something that where gravity is so strong that you cannot escape from. This is the point of no return, right? So anything from inside can no longer escape from the black hole anymore. So this is the event horizon. As long as you're outside the horizon, fine. You can come as near as you want and escape later, fine. But as long as you don't cross, once you cross inside, you are lost inside forever. You can never come out anymore. This is the event horizon. Okay. At this part, right, outside the horizon, there is an interesting distance, which is what we call the photon sphere. So a photon sphere, right, is a distance outside the black hole where it is possible for light to orbit around the black hole as if it is a satellite orbiting the Earth, right? So that is also interesting by itself because the light is orbiting around the black hole, so it is not escaping, right? But yet it is outside the horizon, so it's just stuck in a loop around the black hole, but it has not yet fallen into the horizon. So this is a second way, which is, so to speak, that a light can get stuck around the black hole. But it's stuck around the black hole, but it is not lost forever, right? It is possible to make the light escape later by reflecting it with a mirror or whatever, right? So you can make the light escape from here. So this is the photon sphere. The ISCO is the innermost stable circular orbit. I will comment about this later, but it's not so important for today's talk, right? So these are the important features near the black hole that we want to understand. So yeah, at this stage, does anyone have any question? Anything in the chat? Okay.
Sir, can you hear me?
Yes, I can hear you.
Okay. I did the calculation, so I thought the event the length should be only 1m because it's gm minus c square, the c square.
No, that is the formula for the converting mass to geometric units. So
like it's like just like normal things, like normal object we see or have to be like photons.
Yes, yeah. For photons is gm over c square.
Yes, gm over c square, and
yeah.
And we consider it as m. And I thought the event what I forgot how to say. I thought it was only 1m. So
I know what you mean. Yes. Actually, it's not a big deal because it depends on the unit that we choose. So uh, for no for the standard unit used in the literature is it will become 2m. But sometimes people just call this mu, including myself. We just call this R0, right? So it's just a
Okay.
choice of units. Yeah, it's no big deal. Okay.
Okay. Okay. Thanks.
Yeah. Anyone have any other question? If not, I'll go to the part 2 of the talk. So we'll be talking about the orbits around the black hole. So how particles orbit around the black hole. So what do I mean by orbit? So orbit is like what we think of when we are talking about the satellites or the moon, right? We have a gravitational system, right? Let's say our Earth or the black hole. And then we can have something smaller that is orbiting around it because it is under the influence of this gravity, right? So a satellite is orbiting around the Earth like that, and our moon is orbiting around the Earth as well. The Earth is orbiting around the sun, okay? And what we'll see later is stars can orbit around the black hole at the center of our galaxy. So this is the relevant to the second half, one half of the Nobel Prize, which is half of the Nobel Prize is awarded to Andrea Ghez and Reinhard Genzel. For the official statement is for the discovery of a supermassive compact object at the center of our galaxy. So the supermassive CO just means a black hole, but it could generally include other objects as well. But most of the time is black hole, right? So they found it by observing the orbits around the black hole, and this is about the orbits, right? So now we're talking about orbits over here, and actually the theory of objects orbiting a gravitational source is actually well known. So everyone, physicists are very familiar with it. So again, I'm showing the equation here, but my main point is that how do we understand a gravitational object based on the orbit? So we have equations to describe everything together at once, right? So if we look at the orbiting object, right, we can measure its position over time, right, how it goes on. Therefore, we can figure out its velocity and its acceleration and things like that. So the acceleration and velocity are linked to the property of the gravitational source through this equation we call the geodesic equation. But of course, there's a non-relativistic limit known as Kepler's law and things like that. So yeah, students taking my class, they will learn more in detail by next month. But the main point is, what I'm trying to say at the end is that if we look at the motion of an orbiting object, we are able to infer the properties of the gravitating source, right? So if you just observe how the object moves around some source, we can actually infer what is the information about the source. And that is important, right? Because black holes, no light can come out, it's black, so we can't see it. What we can see are stars, right? There are many stars in the galaxy that are moving around. So if we happen to find stars orbiting around the black hole, right? So we just need to follow the movement of the star to infer the presence of the black hole at the center of our galaxy. Okay, so this is how we identify them. Now, orbits, of course, happen for all kinds of everyday objects. By that, I mean our Earth, our planets, the moon, solar systems, and things like that. But for regular objects such as the Earth, right, orbits going around planets are usually very boring. They are elliptical in shape, right? So they are almost always elliptical in shape. So they can be more and more round or more and more elongated ellipse, but essentially they are approximately ellipses, right? So these are orbits around regular objects like stars. Then because the reason they are boring is because, the gravity is quite weak. So not much things can happen with a weak gravity. But if you talk about stronger gravity, right, such as orbits near a black hole, then more interesting things can happen. For example, you cannot have a circular orbit that is too close to a black hole. This was the ISCO I was talking about, the innermost stable circular orbit. So this is at unit 6m, by my choice of units. So at that distance, you cannot have circular orbits that is smaller than this limit. And anything smaller, well, it will eventually fall down into the black hole, right? So these are unstable orbits. But as long as you're outside, you can have circular orbits around the black hole. Okay, so that is the ISCO that popped up just now, right? It stands for innermost stable circular orbit. Okay. Then for more general types of non-circular orbits, you can have more and more weird and complicated shapes, right? So these are not just simple ellipses anymore. You see that the orbits can make loops around the black hole and then come out again and then loops. So these are called the zoom and whirl behavior by Levin in this paper. Okay, so let me show you all the other more possibilities of orbits. So this is a paper by Jana Levin and Gabriel Perez-Ghez. This paper, so they plotted the different kinds of orbits, but they do not draw the black hole. Basically, the black hole is at the center, right? So as you can see out here, right, if you're starting out from very far away from the black hole, so if you're far away, the gravity will become weak, and it looks more or less like an ellipse, right? So that looks quite a normal orbit. But as you get closer and closer, right, the gravity becomes stronger and stronger. Even though you're outside the horizon, you are not falling inside, but the gravity is still strong around there. So it will start to make loops around the center, and then until it comes out again. And then if you are thrown far away, it's back to weak gravity, so it's ellipse, and then you make loops, and then out again, and then loops, and out again. Right, so that there are many different possible shapes. You can have 4 lobes or 2 lobes or 4 again. So the full paper itself has more. They show you it's more complete, like 3 lobes and things like that. So hang on, yeah. So these are possible because it's just because the gravity is stronger, right? So when the gravity is stronger, when you're pulling an object with a strong force, it will accelerate faster. So when it accelerates faster, it can make loops around the black hole until it gets thrown out again, and then it will come back again and make loops. So this type of orbit can never happen around the Earth or the Sun, right? And usually for ultra compact objects such as black holes, you can do that. So let's see the time. Okay, so now let's talk about the Nobel Prize, which refers specifically to the black hole in our galactic center. So I don't know how many people understand the meaning of galaxy or heard of it before. So let me quickly explain, right? So galaxy is a collection of stars. Our sun is a star, and there are many other stars around. And all of these stars, they usually live together in collections called galaxies in the universe. So our galaxy is called the Milky Way galaxy. So our Milky Way galaxy is a spiral galaxy. Okay, so I think I suddenly remembered, anyone who has played Mass Effect will be very familiar with the galaxy map, right? Our local cluster is here, right? So we are nearby one of the arms, not at the center. So the center of the galaxy is usually drawn like very bright. It is because there are many stars living together there. So this is our galactic center, right? So our galaxy is here, and sometimes people say that we live in the suburbs or the outskirts of the spiral galaxy, right? And this is the city center. So city center is a very active and busy place. There's many stars there, a lot of activity happening there, city center. So based on based on current evidence, what we know so far is there exists a black hole right at the center of our galaxy. It is called Sagittarius A star because from Earth is in the direction of the Sagittarius constellation. Okay, so the prize given to Genzel and Ghez is to observe the orbits of stars around the center, and then there's a supermassive compact object at the center. Now, so I was saying, right, this is the city center. It's very busy, hustling and bustling, all the stars going around, and there's a lot of dust and gas everywhere. So it's actually a very messy area. So in order to actually observe individual stars orbiting around it, right, it's actually a very difficult job. So you need very advanced, observational methods and techniques, and you need many people to work on it, lah. So I'm showing this slide. Is like this is the paper, like talking about one of these works, and you see the author list. They have many names on it, and here you can find Genzel's name here, right? So it's most of the time it's usually a collaboration between a big research group. And even Andrea Ghez group looks like a smaller team, but still a lot of names over there. And yeah, it is not an easy job to observe the motion of the stars, but they managed to do it. So what they do was they, from the year 1995, right, because the stars are traveling over very, very long distances, right? These are like millions and millions of kilometers long. So the stars traveling over very, very long distances, and you need to follow them over many, many years to see how they move around the center. Okay, so they actually observe the motion of the stars over many years, and this is what they got. So let me start the video from the beginning. Okay, so the start of the video starts from the year 1995. So they started this observation since the year 1995. You can see here all the stars with their labels S017, S023, all those things. And as the year goes on, we follow how they move, right? So we follow their orbit. So let's play the video, right? So we see it from as the years goes on, right? The stars orbiting around something that is at the center, which they label as this cartoon star here, right? So they observe around from 1995 until essentially this year, right? So you can see how the stars orbit. Okay, so in particular, we can identify this particular one, which looks very elliptical, which is in agreement to the theory. Okay, so this is the the observation made by the team of Genzel and Ghez. Okay, so yeah, so that is their work, right? So by observing all these orbits, right? So what you can do is, yeah, you can actually follow, and as time goes on, you can figure out what are their velocities and things like that, and they can infer, you know, what is the thing that is right at the center. There's a supermassive compact object, so something having a very strong gravity that every other star seems to orbit around it instead of each other, right? So if there's nothing else, like then objects tend to orbit each other. So this one must have some kind of dominant gravitational force. Okay, yeah, so that's the video. Any question?
I have a question.
Yes.
So like at the beginning, you said that there are many shapes of the black hole. How do you decide like which shape is possible? Is it like solve some PDE system to decide the curvature of the surface or something like that?
Yes. Yeah, so
And,
it's just the ODE.
okay, and also you also mentioned about like the droplet shape with a acceleration, but what's our acceleration, like another black hole?
So that one, okay, your first question, yes, it is an ODE. So every ODE, you know, once you put in the initial condition, you have a unique solution, right? So once you do that, you can are able to actually classify all the topological. So these are like the topological properties of the thing. So if I were giving a more mathematical talk, it will be interesting to explore more. For your second question, the source of acceleration, that one is like this is like, so is okay. So there are two ways to put this. So the first way is to say that, okay, if you write down a metric that is describing an accelerating frame, so you're already starting with that situation, and then you solve the Einstein's equation, so you get this solution. Okay, so the technical terminology is we are solving this on the background of accelerated anti-de Sitter space. So anti-de Sitter space in the accelerated frame. But the physical meaning of this accelerated frame, right? You can actually calculate the right-hand side of the Einstein's equation, which tells us information about the gravitational sources, right? So the gravitational source is like usually is some kind of cosmic string or a cosmic strut that will pull the system up. If I'm drawing this picture in this orientation, okay. So I don't know if that makes any sense, but in the space-time metric, you can calculate that there's a conical singularity over here, and this means that there is something that is some mass or some cosmic string, people call it, that is pulling the system up.
So having an acceleration is pretty normal.
I mean, normal in what context? I mean, having an acceleration. Yeah, it's normal in the sense that you can just easily write down the metric for it.
Okay.
So you can write down accelerating. Yeah. Okay.
So
Yes.
So about the model you made, the one like fluid. So
yes.
If it has itself has some acceleration and it finally tears apart, and does it have a minimum mass? Like, does it need the minimum mass? So, like if the
minimum
mass
of the black hole.
yes, the minimum mass of the black hole.
Actually, in this context, the mass here is undefined because this is an infinite size black hole, so the mass is infinity. Yeah.
Okay, but if so this model doesn't need like a minimum mass.
Well, if you will need
which larger than the regular, like if just one black hole like a mass point, we treat it like a mass point, and a black hole should have the minimum mass, right?
No. Even for normal black hole,
or...
actually, even for normal black hole, we have no minimum mass.
Okay.
The mass can be as small as you want, as long as it's non-zero. Okay.
But the radius should be infinity small, or
yeah. So if you're talking about like the short shell radius, right? Let's say this. Okay, so as long as m can be anything and any number non-zero, so if you times 2 to it, then that is the radius. So it can be infinitely small, yes. If it is dependent on the mass. So if the mass is small, the radius is small. If the mass is very, very, very tiny, the radius is also tiny.
So as the mass goes really, really tiny and it's over the c square, so we can know that the m is much tinier than we
right.
can observe, right? That's the idea.
Right, that's true.
Okay.
But, yeah. Okay.
Okay, thanks. But I mean, so if we have to get to a does it need to? So if the mass is really small, and can we conclude that there is a event horizon that which between that space where light can't escape?
Yeah. So it's still the same situation. So even if you have a very, very tiny black hole, then it just means that the event horizon is very, very small.
But if there's a photon or any particle inside the space, it can't escape too.
Yeah, so it's stuck in a small area. Yes. Yeah, so that is basically what happened. Although if you are too small, right, we have to be careful because when something is very small, small things you need to talk about quantum mechanics, right?
Yes.
Yeah, so then you need to incorporate quantum mechanics into this situation. So you need to treat this carefully. I mean, you don't need quantum gravity yet, but you still make sure the quantum wavelength is consistent, and this is how you see, maybe due to if the black hole is too small, and you can say that due to the uncertainty principle, you can see the wavelength of the black hole will give an uncertainty spread. So there's a chance that the photon cannot fall inside this event horizon. This something like that. You know.
And that's somehow why the relativity and quantum mechanics is not is
not
like
compatible. Yeah, it's not.
Yes.
Yeah.
Okay.
Yeah, that's true. So that's another one of the unsolved problems here.
Okay, thank you.
Okay, so I think I have approximately 10 minutes left. Which can now talk about the singularity inside the black hole, right? So again, this the technical stuff. Ignore this, is just decoration. But this is called the Penrose diagram, which is now the winner of the Nobel Prize. So the other half of the Nobel Prize 2020 is awarded to Roger Penrose. The statement is for the discovery of black hole formation that is a robust prediction of the general theory of relativity. So I'm going to explain in this section essentially what this means. Okay, so so this is Roger Penrose when he's young. So I made a comment that young Penrose looks like Colin Firth. And so in this chapter, right, I'm talking mostly about theorems related to black holes. So we are back to theoretical physics. So before mentioning the singularity theorem, right, which is by Penrose, I mentioned very briefly about the no-hair theorem, which is also important for black holes. Another term for it is also called the uniqueness theorem. This is proven by, there are many different theorems. So among them are proven by Wittgenstein, Israel, Wheeler, and all those other things. So what does it mean, the no-hair theorem? So what it means is that all black holes are almost indistinguishable, right? So if you have a black hole that is 10 million tons, we have this event horizon that is perfectly spherical, okay? And then you have another black hole that is also 10 million tons. Then these two black holes, you cannot tell them apart, right? If they change place or whatever, you don't know who is who, right? And the reason why is, you can imagine in a simple way is, okay, if I try to distinguish one with the other, right, maybe you can give it a name tag, right? So if, imagine trying to put a name tag on the black hole. If you put a name tag on the black hole, it will drop inside the horizon, gone, right? And the main reason is the horizon, right? So if you put some identifying feature, give it to a black hole, it will be lost, right? So black holes all look the same. You cannot tell them apart. The famous quote by Wheeler or Wittgenstein is, they say that black holes have no hair. Why they say that is because, well, I can explain this in this picture, right? If you have no hair, right, you look the same. You cannot change your look. For example, Patrick Stewart, you know, Patrick Stewart, he looks like Patrick Stewart in every movie, right? So he always looks the same. He's just Patrick Stewart, no matter what movie he's in. But if you have hair, if you have costume, and you can change your makeup, then you can look very different. So this is Tatiana Maslany. She plays like 5 different characters in the show Orphan Black. So she looks super different, right? So this is why we call it the no hair theorem. Okay, but this is not proven. So this is not Penrose yet. So now I'm going to talk about the singularity. So what is the any question? No. What is the singularity? Now I've been thinking how to explain the concept of singularity in non-mathematical terms. Turns out it's not easy. So one way I can think of is to show you this, right? Basically dividing by 0. So if you try to divide by 0, you get a math error. So that is my way of saying what is a singularity in the simplest possible language. And I want to put it this way because I don't like the way that other people put it in the online articles or the on YouTube or things like that, right? Like people like Neil deGrasse Tyson, they will say things like, oh, a singularity is where the fabric of space and time has been torn apart and reality has been broken down and everything goes weird. And I'll be like, relax, bro, relax. So it's like, it's not so dramatic, something like that, right? It's not as extreme as that, but he's not wrong. Singularities are problematic, right? So I want to avoid being that over dramatic kind of description. And what essentially singularity means is that there's some area of some mathematical operation that you cannot do, right? If you ask a calculator to divide by 0, it will just say, no, I can't do it because it doesn't make sense, right? So because if you believe Neil deGrasse Tyson, right, if you ask your calculator to divide by 0, which I'm going to do now, like if I press enter now, then this calculator, the fabric of space and time will collapse into a black hole, right? It doesn't make sense, right? So so that is some gist of singularity. So for the black hole, the singularity happens, one among them is regarding the curvature. So I did not talk about space-time yet, but according to Einstein's theory of gravity, right? We can treat space and time like some geometrical object. So it can be flat or it can be curved, right? And we can calculate a formula for its curvature. So for example, for the Schwarzschild black hole, you can calculate a curvature quantity that is obeyed by this formula. Again, don't worry about the details. I just want to emphasize that we are dividing by something involving a radius. So according to this formula, the further away you are from the black hole, the curvature is smaller. But if you get closer and closer towards the center, the curvature is higher and higher. But right at the center itself, you are dividing by 0, right? So students will say it's infinity because dividing by 0 is something like infinity. Okay, so that is the singularity here, right? You are essentially dividing by 0. So that is a problem because although, right, I refrain to be as dramatic as Neil deGrasse Tyson or something like that, right? It's not like the fabric of space and time torn apart, but the problem is this, you know, our equations, right, describing the Schwarzschild black hole or Kerr black hole or whatever, it is supposed, at the end of the day, supposed to describe something happening in space or something happening in nature, right? So nature is nature, it exists, right? So, and is ostensibly self-consistent. So, and our equation is supposed to describe something that is self-consistent. So then when you have something like a singularity, right, that means there is some math error. So how can nature give you a math error, right? So it kind of doesn't make sense. So that is the problem why singularity, you know, if you encounter singularity in our equation, physicists will have to be extra careful to figure out what is going on. So usually, right, when physicists encounter singularity, which is what happens when they found the solutions in the 60s before Penrose proved this theorem, is that, okay, maybe the calculations are not that accurate. Because normally theoretical physicists, in order to solve their equation, they need to do some simplification. So if you simplify too much, then you get something that is not accurately describing what is actually happening. So people were suggesting, okay, maybe this is what is happening about black holes over here, right? So for the black hole, you know, the formula for this possibility, we say that, okay, maybe there is, the singularity doesn't actually exist inside a black hole, or black holes may or may not exist. That also calls into question, right? And at that time, we already believe that, you know, black hole form because a star form, when a star dies, right, it stops burning fuel, it will collapse gravitationally, and once it collapses, it will compress, and you form a black hole. Okay, so maybe our theoretical calculations involving this collapse is not accurate as what these people are suggesting. So that is one possibility. But then Penrose and also Hawking, they proven otherwise. Okay, so for those who are not familiar, we can ignore the technical details, but I just want to show you because that is Penrose's result, which he won the prize for partially, right? And Hawking was also contributing to these theorems as well. So what Penrose did was, okay, if you're talking about not accurate, right? Okay, so fine, let's be accurate. Let's consider the most general situation, and then let's see whether it is possible to have a collapse that does not produce a singularity. So the simplest way to explain is by pictures like this, right? So Hawking and Penrose, they consider the most general situation. Then you have collapse. So you can have any configurations, right? For many different pieces, they've blocked together. And because all these objects are gravitational systems, so gravitational systems, they pull things together. So what they found was, no matter whether or not you put the simplification, you know, technically, I mean spherical symmetry or axis symmetry, even if you ignore those simplification, right? In the most general case, you eventually things will collapse and you will have to form the event horizon and the singularity. So it seems to be that is the generic feature of Einstein's theory of relativity. Okay, so that is Hawking's theorem. So he proved that it is possible no matter what you start with, right? Whether you allow the simplification or not, then you know, you end up with the singularity. Okay, so singularity must exist due to the gravitational collapse. So they have proved that singularities are real. But then, okay, so we proved that the singularities can happen. Then we are back to our original problem, right? How can nature have a math error? So the best loophole at this situation, what we can think of is that, well, at the moment, all the singularities that we know exist inside the black hole. Okay, so they are hidden behind an event horizon. And as long as they're behind the event horizon, nothing can come out. In other words, no information can come out. Or another way of saying is that our reality is cut off from the reality inside here. So that means we are hidden away. Even if there's a singularity, we are cut off away from this singularity. So this is what is called the cosmic censorship hypothesis or conjecture by Penrose, proposed by Penrose. So yeah, he proposed that singularities are always hidden by the horizon. And as far as I know, I have not checked recent literature. It has not been proven yet. So so that means, right, what he proposed is that if there is no singularity that is exposed to the rest of us, right? So yeah, so a naked singularity, an exposed singularity. So basically what he means is that a singularity is censored. Even if there exists, it is censored away from us, right? So if there exists a singularity, another way is to think about this, right? This scenario, okay? We are not supposed to be able to observe math errors in the universe, right? Our universe seems to work perfectly well, you know, around us in everyday life, even in our solar system. But if there's a black hole, according to Penrose theorem, there exists a singularity inside. Okay, now even if you want to look at the singularity, you need to go inside the black hole to look at it. But even if you can do that, once you go inside the black hole to see it, you cannot come out anymore to tell others about it, right? So you are lost inside with it forever, right? So this reminds me of the saying, you know, in movies, right? Like in the spy movies, you know, the spy is hiding a secret, and then someone is asking the spy, what is your secret? Then the spy will say something like, I can tell you, but I will have to kill you, right? So it's something secret of the universe that is censored away from us. Okay, so what we do know right now is, thanks to the theorems of Hawking and Penrose, is that yeah, the singularities do exist. It's just that we can't see it, right? So that also speaks to the power of mathematics, that we are able to access regions of reality that we are not able to, you know, access otherwise. Yeah, so time is dragging along, so I will go through part 4 very fast. Just to mention a quick thing, the past 10 years has been very exciting for research on black holes. In 2015, we have directly detected, you know, gravitational waves. That was quite exciting. And then last year, we have first seen the first direct image of a black hole that is in the center of another galaxy, M87, not ours. And I believe right now they are working on observing the black hole in our galactic center, the one that all the stars are orbiting around. So they are working on observing that right now. It's a bit harder because the mass is smaller, so the size is smaller, and you know, you need is almost the same challenge at observing this galaxy, which is 50 million light years away. Yeah, and then so this one is open problems. I already kind of mentioned briefly already, is the problem of quantum gravity. It is not compatible. You know, the theory of gravity and quantum gravity is not compatible, so it's still an unsolved problem. And another, yeah, so holography is, in fact, there's many things to say about this. It is enough for a subject for a separate talk. Besides that, I think that's all from me, just within time. Yep. So thank you, everyone. Do you have any question?
Me, I have like maybe 2 or 3 questions.
Sure.
So when we consider about gravitational acceleration, and how do we treat the Earth's mass as a mass point, and is that the same way we treat the singularity?
What do you mean gravitation? Oh, so like, for example, the Earth's planet, and then the object.
Yes, when we just treat, sometimes we treat the mass of the Earth like a mass point.
Right.
Is it the same idea that we treat the singularity?
Correct. In the sense that as long as we do not we do not set r equals to 0, then it's fine.
Okay, so it's just the ideal model. But,
it's just an ideal model, yes. So
but is singularity also an ideal model, or it can exist? Because you said it does exist in nature.
Yeah, so that is the proof of Hawking and Penrose. So it does exist in well, it exists if you assume general relativity. Okay.
So what Hawking and Penrose basically did is to prove the existence of the singularity.
Correct. Yes. Yeah. Although I should mention, yeah, it's assuming general relativity, and people right now still believe that, okay, actually if you go r is small enough, the quantum mechanics will be important. So maybe we need to replace, if the distances are small enough, we need to replace the formula with something from quantum mechanics. So that is another to avoid singularity.
Okay, and because I hadn't learned quantum physics yet, so
yeah.
Because do you know the white dwarf, the kind of, I don't know if it's called the white dwarf, which is
white dwarf.
Star, like a star which is dead and its mass is under the Chandrasekhar the limit.
Yes.
And, so it just turns into a white dwarf.
Right.
And you answered me before, like everything could be like a small black hole, because the mass can be really tiny.
Yes. So is the reason why is that why you're asking the minimum mass?
Yes, because it's a bit confusing. So.
Yes. So I understand. I get what you mean now. So actually, what's happening is everything I'm talking about today is I'm ignoring quantum mechanics. I'm ignoring quantum mechanics. But there are two ways to have a tiny mass black hole. So so white dwarf is there is a minimum mass because of quantum mechanics, right? The Pauli degeneracy pressure will prevent the collapse from continuing further on, right? So.
Yes, I know that. Otherwise, the most space of the atoms are empty, right?
Right. So, but okay, so white dwarf. Okay, we put aside the white dwarf. So let's say we have something that is higher than the Chandrasekhar mass, and then we collapse and we form a black hole, right? So this black hole is very large, okay. But
yes.
But what's important to me is, okay, the black hole is large, but it's formed already. What can happen with a black hole also is Hawking radiation. Have you heard of Hawking radiation?
No.
So this is another discovery by Stephen Hawking, is that the black hole, right, it can actually emit radiation. So electromagnetic radiation, massless particles, massive particles, things like that.
And that's how we observe it, right? Or there's other way?
We cannot observe the black holes in space through Hawking radiation because it will be very small. It's inversely proportional to the mass of the black hole square. So if you have a stellar mass black hole, then 1/m² will be a very small number. But if we wait long enough, right, it will slowly emit black hole because of conservation of energy. So radiation carries energy out of the black hole. So that is that is one way you can escape from the black hole as Hawking radiation, but is in the form of radiation, right? So it carries energy out of the black hole. The mass is getting smaller. So if the mass is getting smaller, the black hole will get smaller and smaller as well. So it eventually becomes small enough until you reach the tiny black hole.
Okay. And there's another, I don't know how to say, maybe I should say suspicion. Like when we turn on the light and we turn off, so the room gets dark again. There's no light. And the reason why we can't keep the room with lights, is that because photons get absorbed by the tiny black holes? Can I say this, or?
No, you mean in our rooms, like the everyday situation, right?
Yes.
Oh no, it's just absorbed. The conservation of energy, the energy of the photon get absorbed by the molecules. So if you shine on something black, right, then
Yes.
it's just get absorbed by the molecule. So it converted into the
So-
vibration energy of the molecules.
So it's only black because it's just absorbing.
Right.
Right.
Yeah.
Okay.
Yeah. Okay.
Okay, I think I'm done.
Okay, thanks for your questions. Yeah, those are great questions. Someone raised their hand, is it? I saw something. No.
I don't think so.
Oh, okay.
Any other questions from the audience?
Yeah, so if you have any question, you can unmute your mic and talk to me. Okay. Or chat. Anything in the chat?
Sir,
Hi.
I have a question.
Yes.
When the black hole is a how to say is a ball on the 3 dimension, then did it is a circle in 4 dimension?
It's a ball in 3 dimension, circle in 4 dimension.
Yeah.
The other way around, right? Yeah, so is that your question?
Yeah. This is the question.
So you're talking about higher dimensional black holes, right?
Yes. Yeah.
Okay. I can spend another hour talking about that. So, So we start with 3 dimension. If you have a ball, right? If we take a slice of the ball, right? So you take a cross section. It looks like a circle. So it's like a projection, right? So so there are many theories for higher dimensional gravity because about 10 years ago, string theory was very popular, so we talk about higher dimensions, and then people talk about like things like brain world, black hole. So our universe is actually in 5 dimensions, and then what we observe as a black hole is actually the projection coming out of the 5 dimension. Okay, so is that what you heard of, right? This type of theory, right?
Yeah. I just see the book about hyperspace.
Oh, okay. Yeah. If you believe that our universe have more than 4 dimensions, right, 3 space and 1 time, then you can have like many more types of black holes. So yes, so you can say that what you observe as a black hole, right, is actually a cross section of a higher dimensional object. And in fact, that we have been working on like black holes in higher dimension for the past 10 years. And I did not talk about it in today's talk. So you will see things like black rings, black Saturn, the even more kinds of black holes over there. The shape and topology will be even more complicated.
Oh, that's interesting.
Okay.
Thank you, sir.
Thanks.
So Dr. Lim, you want to comment a bit to the students, okay, what kind of mathematical machinery they need to learn to do this research in black holes?
Oh, well, starting from the beginning, calculus is definitely important. And then later on, learning how to solve, differential equations, differential geometry, and a bit of it lah. And maybe a bit of topology. So starting off with that. So differential geometry, topology, differential equations, PDEs, basically. Yeah.
So in this research, okay, how much theory of these quantum fields are required?
Not much actually. So everything I was talking about today, right? I have been ignoring quantum mechanics, and so you do not actually need a lot of quantum mechanics here if you want to focus purely on gravitational physics. Although on the other hand, it would be worth if I'm answering for students, right? Students should remember to keep in mind the quantum side of things as well, because the classical non-quantum physics, non-quantum gravity is more or less well understood already. So we know almost everything about it already. The open problems and unsolved problem is to combine quantum physics with relativity. So in that sense, yes, it would be good to know some quantum mechanics.
By the way, actually, I mean, I know Penrose as a mathematician, quite a long time ago, and I think he's famous for his something called twistor theory.
Oh yeah.
So is that anything to do with his work in black holes?
No, twistor theory, I believe, is one alternative formulation of gravity, right? Where the space-time has no, you include torsion in your connection, right? Something like that.
Actually, I forgot already what is that about.
Yeah, it's also like it's a sort of a topological type of formulation for gravity. So it's not I don't think it's very related to the Penrose theorem for I mentioned today lah. Because Penrose for his theorem, I mean the one I was talking about, the singularity, is we are meant to assume purely Einstein GR. So
Okay.
I have so someone raised their hand.
Yes, there's a.
Partif, hi, you have a question?
Hi, yes. I'm very new to black hole and everything, and I just wanted to ask that if a large star near our sun
Yes.
becomes a black hole, will it
Yes.
be able to eat our sun?
No, as long as you're outside the horizon. So
What if the sun goes inside the horizon, will it be able to eat it then?
Yes. If for some reason the sun goes into the horizon, yes, then it will get eaten.
Okay. All right. Thank you.
Okay, thanks. Yeah, thanks for the question. Because another thing I did not mention, right? Black holes as gravitational objects. So as long as you're outside the horizon, it behaves just like any other gravitational system. As long as you do not fall inside. Once you fall inside, gone. Yeah. So yeah. So thanks for the question.
Another question.
Yes.
So you said that you basically ignore the quantum theory.
Yes.
So is it that from Einstein till now that all the models about the black holes we do, and we normally use the traditional mechanics theories about the gravitations?
Yes. Most of it, yes. Yeah.
But are there also some models like we use the quantum theories gravitations to explain the black holes?
For just black hole itself, not necessarily, but like just now I mentioned Hawking radiation, right? There are a few ways to describe Hawking radiation. So yes, so for Hawking radiation, there's one example where you need quantum mechanics. So like it's due to the energy time uncertainty principle that you have a particle antiparticle for. So that's how the Hawking radiation gets formed. And in fact, there is a quantum gravity model description of Hawking radiation as well, a second description. In the 70s, people were trying this attempt to quantize gravity using path integrals. We call it Euclidean quantum gravity. So you can also use that to explain Hawking radiation. Yeah. Does that answer your question? I see Peter also has a question.
Okay, I want to make a comment about this about the party's question. So it is not that important whether the star becomes a black hole or not. If the sun is on a trajectory, on an orbit that collides with the star, well, then the star will eat the sun. Never mind whether it is now a black hole or not. So if two stars collide, then they collide. Whether one is a black hole or not, it doesn't matter. And if they do not collide, as long as the stars are far enough apart, or the star is far enough from the black hole will not eat the star. So there's not so much difference between a black hole and the star. Also, our sun eats comets. It can, if a comet or an asteroid or whatever goes in the direction of the sun, then it will be eaten. If it is far away from the sun, or sufficiently far enough, or has enough speed, it will orbit, right?
Yes.
So if it any particle comes too close to the sun, it will also be swallowed by the sun.
Right.
So this is somehow similar to the black hole, and that's what Yan King mentioned at first. Black holes are no vacuum cleaners, so they do not suck everything in. They just eat you if you come close enough and have not enough speed.
Right.
Similar just to a normal star. Also, a meteor can't collide on the Earth, right? So also the Earth always eats some asteroids, something like this, right? So every day we have tiny pieces of rock that fall on the Earth. So even such a small object like the Earth stays growing and eats up material from space without being a black hole.
Yeah. Yeah, as Peter was making his comment, I was reminded in 1994, right? Jupiter ate a comet, and we watched it live, almost live, basically. So the comet Schumacher-Levy, you can Google. In I believe it's 93 or 94, a comet fell into Jupiter, crashed into Jupiter. So before crashing, it broken into pieces, and then it got eaten by Jupiter, the planet Jupiter.
All right, thank you very much.
Okay, thanks. Anyone have any question?
Kaishan, you have a question?
Hi, Professor. Can you go back to the slide with event horizon, photon sphere, and ISCO?
Okay. Yes. This one?
Yeah. May I ask what kind of mathematical properties give rise to these different regions? As in, why are there like 3 special regions instead of like 4 special regions or 5?
I can actually relate this to what I was talking about in my class. It's basically just like the well, maybe not, but it's like the unstable equilibrium. This is a critical. Okay, so okay, let me start again. The mathematical properties you mean? Okay, so let me show you this equation, right? So this equation, it will give you the we call it the equations of motion for the orbit. Okay, and from this equation of motion, we can actually calculate something similar to the conservation of energy. And from there, by observing the conservation of energy, right, as we know, we have the K plus, so this thing is the total energy. So something similar to this equation. I don't know if you can see. And by studying this term here, we can identify all these important regions, at least these two, these three. So 2m, 3m, and 6m. Does that answer your question? It's basically by by observing this term over here.
Okay, I can't see it.
Wait, let me. Yeah, the equation familiar to most, everyone here, I guess.
Oh, okay.
Yeah, so it's just by observing the, or to put it in a more simple way, or long story short, is by studying the equations of motion of particles. And we can have two types of particles, like normal everyday objects, we call it time-like particles, like planets and stars. Second type of particle is photons, light, right? So we can have similar equations for two of them. So if we study the two of these equations, we can identify these regions. So these regions. Yeah.
And then why is there a gap between the event horizon and the photon sphere?
So because it's two different things, actually the photon sphere, the equations of motion will tell you about this information, but this part, right, the event horizon happen is because of another aspect, which is the metric of the space-time, right? So I mentioned we need differential geometry to understand this. So so this is where something goes wrong in the coordinate system of the manifold, right? So it's like you're combining two different descriptions together to have this overall picture. But the physical reason, okay, so that's the math. What I just said is just pushing the answer into math, right? Okay, so let me, I guess, explain the intuitive reason is because it's just the photon sphere, right? It's actually not a unique property to black holes. Okay, that is in fact the most important thing I should have said. Photon sphere happen is just because of gravity being strong, right? So if gravity is strong enough, right, it's able to bend the path of light, you know. We call this gravitational lensing. So if the gravity is stronger, the bending is even more. It will bend the path of light even more. So if you shine a light near something with strong gravity, in fact, our sun can do that, right? If you shine a light past the sun, right, the sun's gravity will pull the light a bit. So if the gravity is strong enough, it doesn't have to become a black hole. If it's strong enough, it can bend it into a circle. Then it can go into a photon sphere.
So outside of this photon sphere, how does the trajectory of light behave?
Generally it's just like well, I guess I can draw something. So if you're for a light far away, right, it will just get bent, something like this. So basically like this. Yeah, can you see?
Okay, yeah.
Yeah, so the light is just...
So the photon sphere is precisely the region where it deforms into a circle.
Yeah, so if you go you bend more, then there will be a critical point where it gets bent into a circle.
Okay.
Something like this. Yeah.
Okay, thank you. Yeah.
I should have plugged in my visualizer. Then I can just swap to.
So I actually have a question. So yep. So I want to put it back to math a little bit about the differential equation. So the math behind this is you assume that particle move according to some ODE, right?
Yes.
And then is it true to say that we have this horizon thing is because if you solve the ODE within this horizon, then it is get attracted to the origin. So which mean you have a stable fixed point somewhere there, right? So it gets sucked into the origin. Is it right to say that?
No, yeah, I wouldn't put it that way. So basically the ODE is the geodesic equation. So yeah, it's basically just differential geometry on a differentiable manifold, and on this manifold you have geodesics on it. It's not necessarily a fixed point. It's just that for certain gravitational system, the interpretation on the manifold is that the geodesics will bend towards the mass, and it doesn't have to be a fixed point. So the singularity there is in fact is not the singularity. In fact, the singularity is defined to be the point where the geodesics cannot be extended.
Oh, I see. So it's not really a fixed point there, but the sort of the vector field there is very strong. Is that
right? Right. Yeah.
All right.
So Ishita has, yeah. Oh, you have another question.
So from the language of ODE, can we say that the horizon thing is something like a absorbing region? So once you enter there, then you cannot leave.
No, because well, yes and no. It depends on how we put it. If we derive the geodesic equation based on a certain coordinate system, right? The horizon is a singularity of the coordinate system. So you cannot solve your equation past the horizon, and just because of the coordinate system problem. But if you patch it together in a different coordinate system, then yes. So what you end up saying is that they tend to attract things towards the horizon, which is the source of the gravity.
Oh, all right. Yeah. All right. I think that's a question. Thank you.
Oh, thanks. Ishita has a question.
Yes. So, like Parthiv, I'm very new to astrophysics. So I just wanted to ask, following up to his question, is there a limit as to how big of a celestial object a black hole can eat?
Oh, is there a size limit of black holes?
No, like to what a black hole can consume, I guess.
Yeah. Well, theoretically speaking, there's no limit, because due to the nature of the horizon, anything can fall into the horizon and can never come out. So it can basically consume anything. And
I can also say something about this, like because our theory for the like small size, small mass black hole are like after some dies and then it can contract to a point, something like that, right?
Right.
But people find that there are like super huge black hole in the universe that if we know the model for our universe at this time, so far, it doesn't make sense that you don't have enough time to let the black hole to grow to that big size. So that's a interesting problem. Why there are the black hole of such a huge size? It doesn't make sense at all.
Yeah. So that is also true. Like in the sense that we are constrained by the realities of our universe. Right now, there's not enough material in the universe to make a black hole grow into this size. Or even if there is, it is so far spread out across the rest of the universe that it doesn't have time to reach the black hole. So I guess, yeah, we can estimate from this consideration, we can try to estimate the largest possible size of the black hole, right? We might need probability to talk about this, like statistics or things like that.
Sir.
Yes.
So I have a question about the explanation which that Ishita asked the question she asked before. So if there's a black hole, we call it A, and there's an object B, which is B is the size of B is larger than A, and when B approaches to event horizon, and so is it begin to twisting like or something else?
So you're talking about black hole A and black hole B, and then they come together.
No, B isn't black hole, just a simple object.
Oh, okay. So
so in which part, like if it's in when B approaches to the event horizon, horizon, and so is the event horizon where the B begins to falling in.
Yeah, so I think yeah, so you have some object B and then some black hole A. Okay. Well, it will depend on how you're talking about this type of situation, right? So so I think it's very simple. So whichever part that goes into the black hole first will be lost into the black hole, and then the rest of it, because it is attached, right? And I can imagine everything will get pulled in. Although what really happens, maybe something is more complicated. It might break into pieces. Maybe some piece might have a chance to escape. Depends on the gravity and the orbits and things like that. But yeah, some piece definitely will fall into the horizon and will get eaten by the black hole.
Okay, thanks, sir.
Right. So.
Okay, anyone else that have any questions? Okay, it looks like this is a really very interesting talk, and then lots of you are very interested in this topic. I think if you want to have more discussions with Dr. Lim, you can email him, and I think he'll be glad to share with you his research and his knowledge. And let's thanks Dr. Lim, and then we'll end this meeting right now.
Okay. Thank you everyone. Thanks for the great questions.
Thank you for the talk.
Thanks. Okay, I will stop recording and stop here. Okay. Yeah, I'll stick around if anyone still wants to have any question. I will stay here. But other than that, yeah, that's all. Thank you to everyone.